last lecture. We're gonna prove Fermat's last theorem, hopefully, in some sense. Just 1 second. So let's first of all recall the ultra patching we talked. The ultra product we defined last time. Then we're gonna take F, an ultra filter. Excuse me, a non-principal ultra filter. Okay. That's first. And then I say I have a collection of a collection. I'm gonna call them A. Sorry. A collection of finite. The most important thing is they're finite sets or rings or modules such that the number of elements is uniformly bounded. Then I can define the ultra product, which behaves rather nice. Let me call it script A. So this was defined to be the product, the direct product of all these sets. But then you quotient now the relation that we say if I have a tuple, so a sequence AN, that's the same. So F equal to another sequence AN prime if AN equals AN prime for all N in an element I in the non-principal ultra filter F. So so in some sense, somehow the sequence in the sequences the majority terms are equal in that sense. So then I can define the ultra filter, and roughly speaking, this is kind of a limit. So I personally like to think of it as kind of roughly speaking, the limit of under F of these ANs in some sense. So eventually the limit, because the cardinality is uniformly bounded, is a limit is basically essentially equal to one of the terms, except that somehow the majority of the terms. So the first, I guess, 15 minutes of today, we'll finish the patching argument. So the ultra filter is used so that we can take a limit, in the sense that even if we don't have a sort of what's it called, sort of system of maps between these ANs, I can still take a limit. So that's usage of this ultra filter. So let's just simplify notations. So let's explain what we have now. So I'm going to write Sn to be weight 2 modulo form on gamma naught n intersect with gamma 1 star Qn. And then of course I localize at the corresponding ideal. Maximum ideal corresponding to this row bar here. And for reason to make things more canonical, I take the dual of this, and I put a frame to add a sort of so that this one carries an action of the frame deformation, which I'm going to call Rn. So this is a universal deformation ring where I allow additional ramification at the sets Qn. And then I put frame at S, and I put some local conditions D, which correspond to the level structure at N here, and also the weight 2. And this one is a quotient of the universal local deformation ring in sort of R variables. I'm going to call this one R log infinity. Okay. And also, we know this space here carries actions of this sort of delta Qn, which is roughly speaking some sort of z, roughly, not quite exactly the same, but somehow roughly speaking, z mod p to the n z to the rth power. But depending on, I guess depending on the parameters I put into this qn here, if some of them is multiplied by p power p, this might get a little bit larger. But that doesn't really matter too much. This actually sort of factors through this part in the following sense. I'm going to rewrite this as, so I have something called Jn, where I have Ox1 through x3 times frame number of elements S. So these will correspond to the dummy framings at S. And because of, and maybe I just write it here, that's the ZP of delta n, the group algebra, can be written as ZP of Z1 through ZR, quotient out by an ideal. I'm going to call IQN. Explicitly, this IQN will be something like Z1 plus 1 to the P to the N minus 1, generated by all i's. All R. Will be generated by all these sort of Z I plus 1 to the P to the N minus 1. So therefore, this will carry an action of ZR, and then quotient out by IQN. Like so. So where the ZI will act on this deformation ring by looking at how the ramification at this QN looks like, and that will act on the space of module forms. And of course, this carries an, I'm going to write J infinity to be the whole ring without a quotient. So I'm out of space, just write X underline and Z underline for this without a quotient. So once I have this picture here, because this is a free formal power series which maps to here and maps to here. So you have a map this way, but it's a free power series ring. So for each of the generator, I can lift it arbitrarily to here as a pre-image of that, whatever the image here. So I can factor, exists a factorization. So I'm going to fix one for each end. There are many choices of such factorization. I just choose one. Exists a factorization. Not unique, but factorization. So this is a picture I have. Now I want to, in some sense, I want to take inverse limit of this whole picture. As I said earlier, somehow there's no these Rn's and these Jn's do form a inverse system, but Rn's do not form an inverse system because for different n, the primes we pick into this Qn, there are different primes. There's no relation for a Qn and Qn plus 1 whatsoever. But we can use this sort of ultra filter limit. In this ultra filter limit, these AN don't have to have any relation to each other whatsoever. I just take a limit. So that's what I'm going to do. Except for one small issue, which is that this ultra limit works really well when these ANs are finite. So that's what we're going to do. So I'm going to, but these are typically not finite. And also I missed one thing, that this, and moreover, this is a very important thing, I should have said it. Moreover, this Sn is a finite free Jn module. And this Sn, the space of functions, tensor with Jn, tensor over Jn with J0, namely you quotient. So J0 is the O of X bar, quotient out by all the, basically quotient out by the augmentational ideal of this group here. So this is isomorphic to S0, namely S2 of gamma 0n of this thing. So in some sense, this when you quotient out the augmentational ideal, you get back to the original one we want to study. But these SNs are somehow, you're starting with this S0, you make it fatter, beef it up somehow. Okay, so now, as I said, I want to make it finite. So for each open ideal A of this J infinity. So for every open ideal, so this, you see, this is a formal power ring, and for any open ideal, of course, this, if I quotient out by this is a finite set, a finite ring. So now I have this whole picture. I want to basically quotient everything out by this A in some sense. So essentially, I'm going to write Sn quotient out by ASN. For now, let's temporarily forget about this Rn here, because somehow when I call An here, or rather somehow if I quotient out by A here, conjecturally you should get a finite set, but somehow you can't quite. So we can't quite prove that yet. So instead, let's forget about these two lines. Hold on a sec. Let's sort of forget about this. I'm just going to use this Jn action and this Rlock action. Okay, I'm going to forget about this. So this will again, so because it maps here, so this one will act here, and this one will also act here. So I'll be looking at these two actions. Let's see how I'm going to do this. So this will be acted on by Jn. So what's this Jn? Maybe Jn, I just write it as J infinity modulo IQn. So that's Jn. And then also modulo this ideal out. So this will act on here. In some sense, I'm going to quotient on the entire picture by the ideal A, except I am going to get rid of this term. And similarly, this will be acted on by something about Rlock. We'll see that in a minute. And for Rlock, well, I mean, somehow the idea is that I want to. It's a technical issue. So okay, I pick an ideal A here. I want to quotient out by A, so this becomes finite. I can quotient this out by A. I think typically this will become finite, but I can't quite prove that yet. So instead, I notice that, okay, when I quotient by A, this becomes finite. This guy is now finite. So I have some finite thing acted on by some sort of power series ring. And therefore, this will definitely factor through my ideal of this guy to some power for some Ka. This, for example, you can take this to be the length of J infinity modulo Aj infinity. In some sense, because this times, sorry, I missed something. Okay, times the rank of Jn Sn. In the sense that somehow basically this action on here can factor through this maximum ideal to some power, as long as power beats the length of this space. Because the maximum ideal definitely acts nilpotently here. If the length of this is, say, B capital N, then you raise to some capital N's power. So that part must act trivially here. The whole point, I just want something here. And then, of course, I always have this surjection here. And the reason I write this is that this is independent of N. Even though I write it here, that's the same thing as rank of J0 as 0. So there's no dependence on N here. And therefore, for different N, this object will be this will be kind of a constant object in some sense. Now I'm going to take ultra product. Write this line and then take the ultra product on the other way. So I take ultra product for our choice of non-principal ultra filter F. Then what do we get? then I have, let's see, let's just write it down. It's not doing anything for now. So this will be acted on by UF of R log. For each n, so for each n you have this sort of this data here. Maybe I should say right. And this is, and what I have over here, this is some sort of constant family. This is some sort of constant collection. And on the other hand, this will also be acted on by UF by J infinity by I Q J infinity. I take ultra product of these. Okay, so after that picture, I just take ultra product of every term. Let's see what we have here. Yes. So this F is any non-principal ultra filter. Of course, for different ultra filter, you will get different answers. But at the end of the day, since we only care about J0, we'll eventually go back to the question about J0. It turns out somehow basically using any ultra filter, you will prove a result for that ultra filter, and then you go back to the same S0 and J0. So that's the idea. So this is you can either say this is the most beautiful part of Fermat's of Weyl's proof, and also the most ugly part of his proof, in the sense that it's so uncanonical, extremely non-canonical. Yet it's probably at this moment, or at least so far, the only way to kind of do this, and it works for everything. So it works for every non-principal ultra filter. Okay, so let's see what are these terms. So here's kind of a note here, because these are IQNs. I want to say that these IQN, as this n gets larger and larger, and you see that the way that you express this, so this is, as n gets larger and larger, so you have zi plus 1 to the p to the higher and higher power minus 1. So this ideal becomes very, very small. So as n gets really large, this is actually this will be a sub-ideal of this A. And then when you quotient out by this IQN here, it's the same thing as quotient out by A if n is large enough. Okay, and when we talk about ultra filter, we say, okay, we can throw away finite many terms. So we threw away the finite many terms we had. So this is just nothing but J infinity quotient by A J infinity. Because once we threw out the smaller n's, this becomes a constant family. But that's ultra filter doesn't do anything to it. In a similar way, this is Sn. Excuse me. So this is what's going on? Okay. So this is just basically J infinity A J infinity, and then J infinity. This is sort of quotient by the Copeland ideal A. And what do I have over here? Well, this is something. I guess something. But note that on each of the finite stage, this guy is a finite free module over here. As I kind of remarked there. So this Sn is a finite free module over Jn. If I quotient by the ideal A, it's still going to be finite free of the same rank. If I take ultra product, so this will be, I'm going to write S infinity quotient A infinity. This will be again a finite free J infinity over A J infinity module. So somehow when I take limit, it's like taking inverse limit, except there's no inverse system. We can still take limit. Okay, so that's that. Whereas over here, because this is now constant, so this is just R log infinity quotient of my maximum ideal log Ka. Okay, so this will act on this one, and everything else stays. So for each open ideal, I can take an ultra product of the diagram I have. Next, then I take inverse limit on A and Ka. I think I had a remark here. Oh, I had a remark here. So maybe I should be a little bit careful here. Maybe I should to be I guess that's okay. Okay, so that's okay. So a tiny technical issue is that why do I have to quotient out by this and then take the alternative? Why can't I just sort of take one map like that? The answer is we can't quite do that, because for each n, for this vertical map, for each n, I only say, okay, I find a map. I find some map that makes the diagram commute. For different n, this corresponding map might be different. So I don't know, like, in general, I don't know whether there's a map from J infinity to R log infinity that sort of works for all n. In fact, there's maybe not a map that works for all n. But when I take the limit, you know that you, at each of the stage, you know, this side, if you quotient out this side by some maximal ideal, then there are only finite many choices from J infinity to R infinity log. And the ultra filter will tell you which choice you have to make, so that somehow the majority wins. Okay, so in some sense, at the end of the day, which J infinity to R log infinity you take, like this, is determined by which sort of ultra filter you choose, non-principal ultra filter you choose. So it's all sort of wrapped up in this sort of logic nonsense. But it doesn't matter for our later purpose, as long as there's a map that makes it compute. Anyways. Huh? Oh, sorry, not my bad. I apologize. Thank you for that. My bad. Terrible. Okay, so now I take inverse limit. So I will get, I'm going to write S infinity to be the inverse limit of this A, of this UF, Sn, A, Sn. Let's see. So if I take inverse limit, now the bottom one, when I take inverse limit, I'll get J infinity. So that horizontally will be J infinity. And up here, I take inverse limit, I will get R infinity acting on this. I have a map this way. So this is the infinite level, what we have. This is sort of the finite level, what I have. Okay. So here comes the upshot of this. Now comes the commutative algebra argument we're going to make. Or maybe I want to make a remark. Remark is that if I modulo, if I have this picture, I modulo the augmentational ideal. So maybe I just want, how much is I modulo everything? X1 through X3S and Z1 through ZR inside J infinity. Then this picture becomes I'll say that. So I guess this picture becomes sort of modulo this, so this S infinity, quotient by this ideal. This becomes a usual S0, or maybe the one without the framing. I guess. Okay. And this is a cannot. So even if you did the ultra patching, but somehow because for each of the AN, Sn, you quotient out by the augmentational ideal IQN, that's the same thing as this S2. So therefore, when you quotient out by these ideals, this ultra-patching system is kind of a constant system. So therefore, you just get back to the space, the way two module forms. So there's no ambiguity in this isomorphism. In any case, what we did is that starting from this module form, I make a little bit bigger space, which admits a local Galois group action and then all these J infinities. And more importantly, this is still finite free. Here's the upshot. Commutative algebra comes in. Let's see. So S infinity is a finite free module over J infinity. So there are 3 S plus R variables. On the other hand, we said it many times. Maybe it's good to kind of make a computation of what this ring is. So local deformation ring, together with the sort of R generators. So what's the dimension of this one? So this is again a formal power series ring. In how many variables? Well, you have this R variables you see already here, and at p equals L, you have 4 variables because there are 3 coming from the framing and 1 additional coming from the crystalline deformation. And at p not equal to L or infinity, you have usually 3 variables coming from the, or rather, maybe or it's sort of 3 plus characteristic, or it's essentially all the characteristic of this G, Q, P, I joint go bar 0. But this is always 0, essentially that. So that's always 0 when p is not equal to L infinity. And at infinity, this deformation ring we can compute explicitly in one of the lectures to get 2. So all of these together, I get 3 times number of element S. So in some sense, these two have the same number of free variables. So that's the most important thing in this lecture. And somehow I guess I want to comment. So this is what very important, that why over here I want to put in a crystalline condition, and over here I want to put in a condition where there's a condition somehow secretly put in, which is sort of determinant of the complex conjugation is -1. Odd condition makes it that this dimension is 2. If the complex conjugation is x by scalar, then it's going to be 0, so this dimension will be much smaller. So that will not, the same argument will not work. Now I'm going to introduce some commutative algebra. Okay. So let R be a Noetherian, commutative Noetherian local ring. Again, this is commutative algebra I'm very bad at, so please. So M is a finite generated R module. So I can define the projected dimension of this M. This is the maximum of N, such that if I put M here, for any N that's equal to 0 for any R mod N, and I greater than equal to N. Maybe I just write it like that. If for any R module N, the X of Mn will vanish beyond the degree N, then this N will be called the projected dimension of M. In particular, if you think about this, if M is projective, that means this X will vanish beyond degree 1. So therefore, projective dimension equals 0, essentially if and only if M is projective. You're right. Thank you. The same thing as R is a free R module. I mean, my M is finite generative, so projective is the same thing as free. Oh, excuse me, locally free. What did I write? Oh, I said local ring. Good. Good. I didn't see a local. Good. Okay. And somehow, basically, this projective is also the same thing as the length of the projective resolution of M. If your M is not projective, you can find the projective resolution of length, say n, then that's the projective dimension n. Another thing. Called depth. That's a maximum of n, such that you can find a bunch of elements in the maximum ideal of R, such that x1 from M, just multiplication by M1 is injective, comma, multiplication by x2 on actually already modeled by x1. This is injective. And you can guess what's next. Dot, dot, dot. Multiplication by xn from M modulo x1, xn minus 1. Is injective. And of course, still this M is not generated by the by the ideal. I mean, this M is not equal to this. Interesting. So of course, I mean, like if x1 through xn M equals to M, you can put in any non-zero x, and the corresponding map is injective because 0 to 0. So in some sense, basically, this x1 is what's it called? A non-zero. I don't know. I don't remember what it's called. Regular sequence. Yes. Thank you. So this x1 through xn gives a regular sequence on this module. Depth is the maximum length of such regular sequence. Now I'm going to show my laziness. I'm going to show my laziness. I'm just going to make a citation to a commutative algebra theorem, which says that this projective dimension of Rm plus the depth of Rm is the depth of RR. Okay, I don't know how this is proved, but it's a theorem. Sorry about that. Sorry, I'm very lazy. I didn't check the proof, but accept that the projective dimension of the module plus the depth is something independent of the module. It's something just about the ring itself. Okay. Maybe before that, it's just something completely trivial. If R is regular local ring, then the depth, I mean the length of regular sequence is precisely the crude dimension of R. Okay, that part I know. That part I know. Okay, and then I have to do the. I apologize for just citing the commutative algebra statement, but we just take faith in this. So I want to apply this to our situation. let's simplify our situation a little bit. So what do I have? I just erased, which I did very badly. So I have J infinity mapped into R infinity log, which acts on S infinity. Okay, and S infinity is free over J infinity. Right. So what is the depth of S infinity as a J infinity module? Well, S infinity is a finite free over J infinity, and what's the maximal number of sort of length of regular sequence? Well, that's basically you just take the and also J infinity is a formal power access ring, so that we know that this is just the same thing as the Crew dimension of J infinity. Right? We basically this is the same thing as J0 direct sum as modules. It's a free module, so that's the same thing as just J infinity as a module over itself. So that's just Crew dimension. Okay. Then we know that would imply depth of. If I want to think of this as infinity as a module over R infinity, I want to look at the maximal length of sort of regular sequence. Well, I could. I mean, so this already give me a regular sequence of length this much. This is what's called. This is R plus 3s plus 1. I already know a sequence where the length is R plus 3s plus 1. Potentially, I might be able to find other sequence where these xi's are in R infinity but not in J infinity. That might make a longer regular sequence, but I'm going to ignore those. So that's at least that much. Okay, I already have a sequence which has that length. I'm happy with that. Now I want to then by this theorem by Auslander and Bachbaum. Bushbaum. I don't know how to say that. What do I know? I know the depth of R infinity. So I know the depth part. This middle depth part is R plus 3s plus 1. It's at least that much. So basically, I know that projected dimension of R infinity, S infinity, plus how should I do this? Maybe do it the other way. Sorry. I'm trying to put things in the right order. So this is the same thing as projected dimension of, let's write it down. Oh, sorry, S infinity plus depth. Okay, we show that this is at least R plus 3s plus 1. And this guy it's a regular local ring, right? My R infinity. So this is, again, the same thing. And the point, see, that's the point. These two rings have the same dimension. So I've ended up getting the same number here. And so this is equal to something plus something a little bit bigger. And of course, I should have said that projected dimension must be a non-negative number, certainly. So that must be 0. And therefore, S infinity must be a free R infinity module. Okay. And then motion back. Done. So this will imply that S infinity, I quotient it out by, let's see, IQ 0, and all these framing variables, also important. So this is the same thing as S2 of gamma naught and dual. This will be acted on by R infinity S, excuse me, R rho deformation ring, which is surjected onto the local ring. IQ0, just a second. IQ0 is just Z1. Okay. So I quotient now by the ideal. And what I know is that the S infinity is a free R infinity module. So therefore, this part, this is free this module. Finite free. I should have said finite free. So this is a finite free this module. And this surjected, and we know the local deformation acting on the space of module forms really factors through the global one, and this y1 yr will somehow this local deformation together with formal variable will surject onto this one and act on this one. So now after we quotient out by these things, this becomes a free module over this ring. This will imply. This also means that this has a free action on this one, and so therefore this must be an isomorphism. Basically this action, because this one, the annihilator of this module is trivial, and anything in the kernel of this map must annihilate that. I don't know what to say. Anything, supposedly there's a kernel here, then anything in the kernel will, when they act on any element in here, will factor through this thing, will kill the corresponding element. But this is a free module over here, so no elements in here will kill elements in here, except the zero thing. So therefore, this must be an isomorphism, and this is a free module over here. So conclusion. In this case, S2 is a finite free we're done. Let me remark a little bit about this. Okay, this is a big case. This is so-called minimum case. I.e., is R log infinity. Or sorry, maybe this is a formal power system. Or maybe you can make it more general, irregular ring. But this doesn't quite come very often in some sense, because you require basically each local deformation ring is a formal power series ring. That hinges on the conditions we put it out. So this depends on, in our special case, we depends on conditions like somehow this row bar, when you have a non-trivial image, this is sort of you require that this image is full FL, but not, but somehow row bar is not unramified at this P for P in S and P not to L. It requires some conditions like this to make sure that somehow all the local deformation we work with are formal power system. So in general, we can't quite conclude this S2 being free over the deformation ring, whatever condition you put. Usually, if the local deformation rings are not formal power series or sort of not smooth, typically the space of model forms will not be free over this deformation ring. But somehow many, but still, and in particular somehow, if this local deformation ring has more component, that's where things get really worse, in the sense that this commutative algebra argument can only make sure that you somehow have full support on one component, or have full support on some component, but doesn't tell you that it has full support on all the irreducible components of R log. So I guess one of the key thing here is that this R infinity here, this is irreducible. Of course, in our particular case, this is a full power string, which is nice. But if you have more than one component, similar type of argument can show that this S infinity will have full support on some components, but doesn't guarantee it has full support on all the components. There's more work to be done to see like whether you can move from one component to another. That's more difficult thing to do. So we just did the very simplest case, but I want you to, I guess, given our limited time, I want you to see a kind of a Taylor-Wells argument, even in the simplest case. But I want to maybe kind of just emphasize again that we actually proved something much stronger. A space model form is actually a finite free module over the deformation. That can sometimes we can use that to do sort of more counting argument sometimes, I guess. Are there any questions about this? I have about a couple minutes. So since I have a couple minutes, let's start writing down some very formal sentences regarding going towards proving Fermat's law theorem, but somehow, supposedly I'm supposed to end the proof in an hour, so let me start doing that. So Fermat's law theorem, I have to write down the theorem. Okay. For L greater than equal to 5 prime has no non-zero interior solutions. So proof, in a sense I won't be able to finish. Sort of proof. So suppose there's a solution. Say A, B, and C. I can require them to be co-prime. There's no harm. I can always require B to be even, and A to be congruent to -1 mod 4. I typically believe these kind of things, although I didn't really check. These are fine. So from these, some elementary way you can probably show that you can always make, suppose there's a solution you can make this B to even and A to be congruent to 3 mod 4. And E, I want to consider a so-called Frey curve. It's an elliptic curve. So maybe say the general theory says that if I have y square x minus a x minus b, E1, E2, E3, then the discriminant of this curve, to see where it ramifies, is equal to 16 times E1 minus E2 square, E2 minus E3 square, E3 minus E1 square. So this is basically truly the discriminant of this cubic polynomial, maybe up to a factor of 16. And in our particular case, let me finish this. Then delta E is equal to 16 times, you see that it's basically A to the 2L, B to the 2L, and times difference of these two roots. So that's a to the L plus b to the L squared. But luckily, a to the L plus b to the L in our situation is c to the 2L. So that's where I guess the Fermat's equation is used. So you put a to the L plus b to the L equals c to the L. That's where precisely where they use. Right. I'll stop here, and after the break, I will talk about the main part of the argument, minus some sort of calculation of the if because. Good. So I'm going to skip over about a page of material, but these are sort of relatively elementary, and you can read them from the notes. So let me just summarize what we know about this Frey curve. So here's a key lemma. And this E has sort of a semi-stable reduction, or excuse me, good or multiplicative reduction modulo any prime p. Okay, so this will imply that the conductor of E is 2 times primes dividing ABC. Okay, that's the first thing. It wasn't difficult, just since I only have one now, I want to get to the sort of content of the proof. Next, to talk about the L-logic representation of this. This is GL2FL. So this is, although somehow this might have bad reduction, but somehow if you look at mod L, where L is precisely the L for the Fermat's law theorem, this is unramified at odd primes. P dividing the conductor, and P but does not divide L. So this is basically because I won't have time to explain, but basically because somehow this P to the L's power divide, maybe I should say, sort of p-adic valuation of the discriminant of this curve is divisible by L. And this is roughly equivalent to what I have here. Okay, so that's the part that we need. So that's why I need some L power here for each one of them. In the sense that somehow, I guess the second part is crucial in the sense that these two are somehow automatic L's power by our construction, but somehow a to the L plus b to the L is an L's power. If and only if basically so A and B and C are the solutions of Fermat. So I need this to be L's power so that this rho bar is unramified at these prime dividing that. Okay. I'm going to skip over the C notes. So now let's get to the, so this is step 1, I guess. Substance. Now step 2 is the modularity. That's basically what this semester is all about. The theorem is that we want to prove, or the main theorem is that the E is modular. I.e., E is associated to a cuspidal eigenform F. Maybe let's get to the next step and then talk about fitness proof and then come back to this. Okay, just because I want just a couple of words where I use things. So let's come back to this theorem in a bit, in about a few minutes. So So suppose that I know already that I already proved the step 2. That's E is correspond to F in the way we set it up. Yet we know that rho bar EL mod precisely that L is the same thing as rho bar FL for the Galois repetition associated with F at L. This is unramified at odd primes P dividing N. Here I'm going to use so-called Ribet's level lowering theorem. My original plan was to somehow ask you to prove this in your final exam. But it turns out that I realized that to prove this, one needs a little bit of knowledge of étale cohomology. Because we define associate Galois in a way of using modular forms and abelian varieties. That doesn't quite work very well with in the way I want to prove this. So instead, in your final exam, I'm going to ask you to prove a level raising theorem, which is going the other way. Let's kind of state the level lowering theorem, which says that whenever you know your rho bar is unramified, then you can find a G of weight 2 such that F is congruent to G modulo L. Okay? Because somehow, at least modulo L, it looks like it's unramified at these primes. So these primes of dividing N shouldn't appear in the level. So under congruence, you should be able to press down the level. So it's called level lowering. And in your final exam, you're going to do the opposite. If your G comes from a lower level, and your local representation looks like something might be able to lift to something which have a larger level, then it does. That part doesn't quite require not as much this information. So okay. So unfortunately, as I said, I couldn't. We couldn't get to the proof of this. Somehow along the way I made a mistake of not explaining étale cohomology. But anyhow. And of course, step 4 is very easy. There's no cast form of level and weight 2, and that's done. So basically, all we need to show the modularity of such elliptic curve, and this is a little bit simpler than general showing all elliptic curves being modular, because this elliptic curve is so-called semi-stable. It's a little bit easier, I guess. We've learned modularity lifting theorems, which tells you that if I know my E, my Galois representation is congruent to another representation that's associated with modular form, then my modular form is sort of modular. But unfortunately, I have to find somewhere to start with. So the starting point is the following. So now I'm going to get to this proof of theorem. So step 2a. So it's a continuous odd irreducible representation rho bar. Oh, my S is all the primes dividing N and infinity. And maybe in this case I need to include 3 in here. Anyway, if this is GL2F3, this is modular. I really need a specific prime to start, namely 3. If I have a irreducible representation of the Galois group with image in GL2F3, this is modular. Even so, I need a big input, which problem itself will take about for my standard, I'm not sure if I can finish it within a semester. So it's rather long. probably I need one needs two semesters for this. So suppose that you have a GLC value of the Galois representation, continuous, irreducible, whose image in PDL2C. We know that these sort of finite subgroups of PDLC can be enlisted. So if it's a subgroup of S4, which is probably the largest one, except for A5. If it's A5, no idea. But S4, yes. If you know that the image is, I know that this is solvable, globally solvable group, and determinant of complex conjugation -1, then it's modular. But it's not modular in the sense of what we are familiar with, namely associated to a weight 2 modular form. It's associated to a weight 1 modular form. Then there exists a normalized cuspidal eigenform called GQ. I'm going to write BQ of weight 1 and level, I guess in this case gamma 1n. You can probably get the information such that this BQ is equal to trace of rho Frobenius Q for Q not dividing them. So weight 1 modular form is a little different from other for weight 2 and up modular forms. Of course, by identifying C with QL bar, you can get a QL coefficient representation. But for weight 1 modular form, the associated Galois representation has always finite image, which is kind of nice in some sense. So the way this is proved is so-called base change. It's so-called cyclic base change theorem, which says that if you have some representation like so with solvable image, then this rho is associated to some automotive form. The way to do this do it step by step, reduce the cyclic case. For cyclic case, they kind of use trace formula to compare things. As I said, that requires a semester or maybe a year of automorphic forms, unfortunately. Granting this, coincidence for L equals 3. Let's grant this. So there's a faithful representation. I'm going to call it psi from GL to F3 to GL2 of Z adjoint root of 2. Root of -2. This is like GL2C, such that choice of this thing is just choice of G modulo. So basically, let me just say this. So I have a residual. Somehow I have a residual representation. I want to lift my residual representation to a characteristic 0 representation. Only in GL2F3, maybe GL2F2, maybe. Only very, very small characteristics, there's a way to do that. For GL2F3, very luckily, there is a representation. Where there is embedding of GL2F3 into GL2, this Z adjoint root of -2, such that you lift it up and they have the same trace, modulo an ideal here, whose residue is F3, and also the determinant. Modulo 3. Okay, let's make it explicit. Oh my god. one of the big issue of writing things on iPad is that do not write a matrix across the page line. Let's see. Now I'm reading -1, -1. Hold on a sec. I only see it here. Just 1 sec. Sorry, I'm writing it across the. So this looks to that, but I'm copying down these. Okay. So I have. So this is an element in. I think of this as an element GL2, F3. I guess essentially, what's the order of this group? GL2 F3. 72. No. Hold on a second. 8 times 6. 48. Group order of 48. So I'm giving 2 examples where they should send. Yeah. And this should be sent to this group. And you can, I guess, one can check by some means. That's there. I mean, you can enlist all the representations. I guess this was observed. So, given row bar, I can compose this. To get a characteristic 0 representation. And then by along the tunnel, you can find a GQ of weight 1 such that BQ is congruent to twice of row bar for Venus Q modulo 1 plus root of negative 1 plus root of negative 2 when Q does not divide n. So basically, the starting point of this is a lot of sort of coincidental things. Moreover, as row bar is ratified at 3, this is because, I guess, the determinant of row bar is cyclotomic. I'm talking about mod 3, so this is mod 3. So the cyclotomic character mod 3 is ramified. So basically, your row bar is itself. I mean, its determinant is ramified, then of course row bar itself is ramified. And so this is a very subtlety. So 3 must divide the level n of G. Next, I consider. So now I want to move from weight 1 to weight 2. So I want to consider a weight 1 level gamma 1 3 Eisenhower series. Write it down explicitly as follows: 1 plus 6 of some sort of character where. So this is typically all Eisenhower's looks like so. And the chi is a mod 3 Dirichlet character. You can find the Eisenhower's. But the upshot is that this 6 is divided by 3. So it's isolated series, but except that it has weight 1, but this isolated series is common to 1 modulo 3. This entire isolated series is common to 1 modulo 3. Now I'm going to take GZ, easy, direct product of 2 modular forms of weight 1. So I get weight 2. This has weight 2. And I guess by counting some sort of ramification stuff, you can show that this actually belongs to, by looking at sort of the central character stuff, you can show that actually belongs to gamma naught n. And moreover, this AQ, the Qth coefficient of this guy, as I said somehow, I'm doing modulo 3, so E will go to 0. E will go to just constant 1 in some sense, if you look at the Q expansion. So that will be congruent to BQ, namely congruent to twice of rho bar Frobenius Q modulo 1 plus root of 2. In some sense, the Q expansion of this modular form looks like somehow this looks like this is a trace of these Frobeniuses. I don't quite know whether this is an eigenform or not, but I know that this must belong to the form of this where we should, after you localize at this maximal ideal. Namely, this is where you could identify this as where this Frobenian, where this Haeckel operator TQ minus rho bar lift X nilpotently. Topologically nilpotently. So in general, localizing at the space of modular forms at the maximal ideal means that taking the subspace where this Haeckel operator minus trace of Frobenius acts topologically nilpotently. And of course, I guess this property looks like that. Somehow, this must belong here. I think I got it right. Or at least modulo P, it belongs there. That means that rho bar is modular. But it may not be. But I mean, this may not be eigenform. I didn't say this is eigenform. But after some multiplication, it might be a sum of eigenforms. Because I guess under this localization, so this rho bar may lift to different forms in characteristic 0. So this might be a linear combination of these eigenforms. In characteristic 0, they're different, but somehow mod P, it all looks like so mod P. So I go all the way around to kind of show that this space is not 0. That's what I want to show. If it's not 0, then this rho bar will have at least one lift. So that shows my rho bar, at least at 3, is modular. As a small 3, rho bar is modular. Step 2b. If for our elliptic curve E, rho bar E3 is irreducible, let me sort of skip the argument here. So, in fact, this is if the character in these kind of cases, irreducible is the same thing as absolutely irreducible. I'm not going to explain this, but it's a simple argument. In fact, maybe let's explain. Let me finish the sentence then. E is modular. I'll say that in a minute. This is basically by step 2a. Rho bar is modular. So by modularity lifting theorem, MLT, this rho E is modular. Okay. But of course, this requires my knowing that rho bar 3 is irreducible. Let me just quickly say this. Explain why I don't have to distinguish irreducible and absolutely irreducible. That's because otherwise, think about what kind of representation which is irreducible but not absolutely irreducible. That basically, up to conjugation, the representation basically looks like the following. If it were irreducible but not absolutely irreducible, it must look like something like this. So Galois group of Q going to F9 cross CT inside GL2 F3. Okay? The only way that something is irreducible but not absolutely irreducible is because it sits inside a quadratic extension of the ground field you consider here and somehow embed that into GL2. It is irreducible, but when you base chain this to F9, it splits up into two characters. So this chi and chi bar. But if you think of this as over F3, it is an irreducible representation because the ground field, you don't have anything in F9. But then in this case, there are two things to consider. So there's a determinant going to F3 cross, and this map, this embedded GL2 F3, and then taking determinant. This basically is x going to x to the fourth power, taking norm. So determinant is the same thing as taking norm here. So norm on F9 is x goes to x to the fourth power. But on the other hand, I have a complex conjugation C here, which I know will be mapped to -1 in F3 cross. And this will be mapped. So then this will be first of all mapped to something F9 cross, and raising to fourth power get to -1. Sorry, start over. So I have this complex conjugation, but then I know this complex conjugation square equals 1. So whenever this C mapped over here must be an element of order 2. It's going from to here, it's raised to the fourth power, it must go to 1. On the other hand, the determinant condition tells you that I need to be odd, so determinant of C must be -1, so that's a contradiction. That's because C squared equals 1, so the C maps over here must be 1, must be order 2. And that map over here must be 1, which is not equal to -1. So that's a contradiction. So we don't have to worry too much about irreducible versus absolutely irreducible. So I guess if for our elliptic curve, if modulo 3 is irreducible, great. But what if the modulo 3 is not the mod 3 representation is not irreducible? There comes the famous Underwell's 3-5 trick, meaning that if one cannot go through this path through 3, he'll go 5. Great work on knowing the prime numbers 3 and then 5. And the generalization of all these is done later on when they consider 3, 5, and 7 for other situations. So assume let's suppose now this is reducible. Sorry, step 3. The theorem is Weyls 3-5 trick. So in this case, we have the following. either E is already modular, of course that part I know how to prove, or if it's modular, if it's not modular, then the following thing will hold. If it's not modular, then at 5 must be irreducible. And not only is irreducible for the 5 torsion representation, you can find another elliptic curve semi-stable such that rho bar E5 is the same thing as rho bar A at A5, and rho bar A3 is irreducible. Then it's clear why this theorem implies what we want. Our modularity theorem. That's because I guess if we don't, if E is not modular, then I guess now I want to use modularity lifting theorems, right? I have a semi-stable even curve where rho bar 3 is irreducible. So then basically step 2b, 2a and 2b says that a is modular, right? Because rho bar 3 is irreducible. So that means that rho bar A5 is modular. The point is that if you want to show something is modular, you need to use one prime to do that. You use the prime 3 to show that A is modular. But then once you show A is modular, we can now mod 5. So rho bar 5 is modular. But this is the same thing as rho E5. And then you use modularity lifting theorem to show that E is modular. Okay. Maybe I should say over here I use the fact that rho A3 is modular. It's a modularity lifting theorem to show that A is modular. And then switch to 5 and do that. And this method has been generalized to deal with other cases where because people use 3, 5, and 7 to do things. So now I just have to prove the 3, 5 trick. Any questions so far? Okay. Proof. A proof of the 3, 5 trick theorem. So first assume that rho E5 is reducible. Then there's a classification of subgroups of reducible. Sorry, never mind. Reducible meaning that the 3 torsion point of the curve has a non-trivial subgroup fixed by Galois group of Q. Yeah. I already assumed that rho bar 3 is reducible. In the same way, 5 has a non-trivial subgroup fixed by Galois group of Q. In other words, that my E will have I guess I can combine the two subgroups, and then E will defines a Q point on x naught 15. Namely, I have this E will have a subgroup cyclic of order 15 defined over Q. All these are sort of fixed by algorithm Q, so therefore the subgroup of order 15 will be defined over Q. And this will define a Q point on x naught of 15. And what is x naught of 15? I guess at time of whiles, it might take whiles some time. But now, just take a computer search. It's that. And the computer search at the same time tells you that the rational points, there are quite a few rational points actually. Okay, let's see what is a good time to. Okay, let me maybe advertise a website here called L function modulo form database.org. So L function modulo form database, and you can all these information can be found there. It's very easy, and people already computed all these, and just okay. So we have these points, and I'm not sure how difficult to see on this website that these 4 of the points. So now I have 8 points. Rational points are cusps, because x naught 15 has 4 cusps, so that takes up 4 points, and other four curves are known to be modular. Or maybe I should say rational point. The cusps, they don't correspond to actual the curves. So E cannot correspond to those 4 points. So the other 4 points, again, this website will tell you which curve this can be. And then to search the corresponding conductor, you see that they are really correspond. Okay? Oh, and I do write down what it is. So the labels are 50A1. I don't know what it means. A3 and 50A4. I don't know what it means. All the if curves with smaller conductor are labeled. So basically, I guess it's always like this. So number theory use some sort of big machine to reduce a question to a finite number of cases, and then computer comes in and solve all the problems. Okay, so that's one thing. So if E is none of above, then rho bar E phi is absolutely irreducible. Right? I discussed the case where rho bar EF is reducible, so that's all the cases I listed. And then now I want to say this is absolutely reducible. In this case, I want to find the corresponding A. So in this case, what am I doing? So okay, I want to find the other elliptic curve, A, which has the same residual representation as this. So I want to consider a y prime phi, another sort of a twisted version of modular curve. It's the following. So as moduli space, so sends R to all the elliptic curves over R. If it were the usual x5, or rather somehow, maybe I should say x prime gamma phi, then I would have to say all the 5 torsions of x to be trivial. But now I want to impose a condition that is not trivial, but rather it looks like my E. So this E5 is isomorphic to A5, preserving wave parity. So this is the inner form. This what did I write? X prime 5 is an inner form of X gamma 5. Well, let me say what I mean by this. I.e. that this is defined over Q, but if I base change from Q to Q bar, algebra closure of this is isomorphic, not canonically, but this is isomorphic of X gamma 5. So it's the same X gamma 5 after base change to algebra closure, but as a Q variety, it looks different. More precisely, it's the inner form of this associated to the following representation: that rho bar E5 so this is a representation, mod 5 representation associated with curve E, and this GL2 F5 can automatically act on as automorphism of this thingy, of this space here, by, because right, this one carries an action of gamma 1 mod gamma 5 in some sense, so this will act on it. And after twisting this action by this Galois representation, you descend it differently to in some sense. A little confused. But anyhow. I'm confused by this, but anyways. Okay, so but one thing is the genus of this X prime 5 geometrically has the same genus as X gamma 5. Very importantly, X gamma 5 is a P1, so genus 0, and I do have a point on X prime 5, which is given by my elliptic curve E itself. It's a rational point. Now here's a general theory. If you have a genus 0 curve over rationals, and there's one rational point on that, then this genus 0 curve is just P1. So genus 0 curve with one rational point will show that this genus 0 curve is just P1 as algebraic variety over P1. So that means that you can find infinitely many elliptic curves satisfying the first condition of B1, namely rho 5 isomorphic to rho E5. Basically picking any point in here. Just picking any point on P1. Minus all the cusps you might see. But there are only finite many cusps. And P1 Q has infinite many rational points. No worries. Okay, that solves the first condition. And it says pick any point on this one. This will give you the A you want. And the 5 torsion point will be the same as the 5 torsion point. Okay. Now need to make sure that rho bar A3 is irreducible. Well, if it's reducible, then all our efforts are in vain, right? If this is reducible, then it's like you're jumping from something which is reducible by 3 to something reducible by 3. It's like to do anything. So let's see which points are the bad points. So let's consider y prime phi 3. So this is a function that sends r to ellipticals over r with phi and c3, where I want a r phi to be as in what I have over there, but then I want a cyclic subgroup of order 3. Right? So if rho bar A3 is reducible, then it must have a cyclic group of order 3 defined over Q. So any points on here will be a bad point. Of course, there's a map down to y prime phi. So this is the so-called bad curve. So this is somehow the good curve. Right? I want to take a point on the good curve that doesn't lie in the image of the bad curve. Q rational, Q points. Not sort of course, it's surjective as algebraic curves, but for rational points, the rational points in here might, typically a rational points here, the pre-image is not it's an extension of some degree, not irrational points. I feel like one can use some sort of Hilbert irreducibility or something. Nonetheless, here's a simpler proof. Yeah, nonetheless, now we have computer. Yet this genus y prime. Oh no! Oh, come on, this is a bloody show off. You can check that the genus of this is strictly bigger than 1. This can easily see that because basically, when you base change to C, this is roughly speaking, gamma 5 intersect with gamma naught 3 of this. And this is something. The genus of this quotient is something supposedly computable. I don't think computer can do this so efficiently. You have to do it by hand. Anyway, nonetheless, this is something you can compute. So it must be greater than or equal to 1. And then I really think this is a bloody show-off. Faulting still, really. I'm not so sure. Sorry, I'm not so sure whether this is truly needed. I really think that some other argument can be done. I really don't think we need this. Okay. Nonetheless, it's finite. So you're essentially removing finite many points from your P1. So the two conditions in 1, the B. And also and another remark is that semi-stable condition. I also need some sort of semi-stable condition. These are so-called open conditions. So after removing finite many finding many sort of points. The semi-stable conditions are open conditions, so you can always find, at least you can find one that's satisfying all the properties. Well, perfect. Done.